We all kind of get averages, right? If you flip a coin a bunch of times, you're going to get around 50% heads. It just makes sense. This core idea is called the law of large numbers, and it's why we trust everything from election polls to big scientific studies. But what if this law, this bedrock of statistics, has a breaking point? A place where adding more data actually makes things worse? Okay, let's get into it. And look, in a perfect world, the law works like a charm. Take rolling a simple six-sided die. The true, theoretical average is 3.5. Now your first few rolls, they're going to be all over the map. But see that squiggly green line? That's our observed average. And as we keep rolling, it gets closer and closer and closer until, bam, it locks right onto that true mean. This is exactly what we expect. More data, more certainty. Simple. So, here's the crucial part. What the law is really saying is that as your sample size gets bigger, the average you actually see in your sample is going to cozy up to the true average of the whole population. It's kind of like a funnel. You pour in all these individual data points, and as you add more and more, they all filter down into one single stable number. It's this powerful idea that we can tame randomness just by repeating something enough times. Okay, but here's the kicker. Dice rolls and coin flips. They're neat. They're predictable. But what happens when we step out of the lab and try to apply this to the messy, chaotic, real world? Can we really trust it all the time? Well, it turns out the law of large numbers isn't some universal, ironclad guarantee. Nope. It comes with some very important fine print, some hidden rules that you absolutely have to follow for it to work its magic. There are two really big ones. First, your data has to be IID, which is just a fancy way of saying independent and identically distributed. Independent just means one roll of the die doesn't change the next one. Identically distributed means you're always using the same six-sided die, you're not secretly swapping in a 20-sided one. And the second one, oh boy, this is the one that's going to cause all the chaos. The system you're measuring has to have a finite, definable mean in the first place. But when you do follow those rules, something amazing happens. Your estimate of the average doesn't just slowly creep towards the right answer, it skyrockets. The chance of your sample average being way off shrinks at an exponential rate. It's an incredibly powerful effect. Now, we don't need to get buried in the math here, but the thing that guarantees this incredible speed is a tool called Hoeffding's Inequality. Just think of it as the mathematical muscle behind the scenes. It's the proof that for well-behaved data, adding more examples gives you a much, much more reliable answer. Really, really fast. All right, but now for the really wild part. Let's talk about the nasty cases, the situations where our entire intuition about how averages are supposed to work just completely falls apart. Professor Tapio Pahikala, whose work really inspired this whole deep dive, absolutely nails it. He talks about wealth. You could go out and survey 1 million people and get a pretty stable average income. But then, what happens if your million and first person is Elon Musk? Your entire average is toast. One single data point can flip the whole table. This crazy phenomenon is the classic sign of what's called a heavy-tailed distribution, like the Pareto distribution. You see, with a normal bell curve, the tails on the end drop off to zero really fast. But with a heavy-tailed distribution, the tails fall off much, much more slowly. And what that means is those totally wild, out-of-nowhere events, they're way more common than you'd think. And this isn't some abstract math problem, you guys. This stuff is everywhere. The Elon Musk effect in wealth, for sure. Stock market crashes, those black swan events. Even in mobile games, a tiny number of whales who spend thousands of dollars make up most of the money. Or think about a self-driving car. It can drive perfectly 1 million times, but that one super rare unexpected event can be catastrophic. Okay, get ready for this because this is where things get really, really weird. For some of these distributions, like the infamous Cauchy-Lorentz, the problem isn't just that the average is hard to pin down. The problem is a true average literally does not exist. It's mathematically completely undefined. Just let that sink in for a second. If the mean doesn't exist, what is the law of large numbers supposed to aim for? There's nothing to converge to. Collecting more data does nothing. It's useless. The average of your sample will just keep jumping around like crazy forever, depending entirely on the next extreme value you happen to find. Averaging is completely, totally broken. So if the average is broken, what are we supposed to do? Well, this brings us to a fundamental challenge for anyone working with data, the constant tug of war between accuracy and precision. The easiest way to think about this is with an archery target. Bias is all about accuracy. Are your arrows consistently hitting the top left of the target instead of the bullseye? That's bias. Variance, on the other hand, is about precision. Are your arrows just scattered all over the board? That's high variance. And it turns out your total error, what's called the mean squared error, is basically just a mix of both. It's your variance plus your bias squared. To be a good estimator, you've got to get a handle on both of them. And this is where we see what averaging is actually good for. In those well-behaved systems, averaging is a fantastic way to crush variance. You add more data, and the spread of your arrows gets tighter and tighter. But, and you have to remember this, averaging does absolutely nothing to fix bias. If your bow is sighted wrong, you can shoot 1,000,000 arrows, but all you get is a very, very precise grouping in the wrong spot. Okay, so what's the moral of the story here? What's the big lesson we should take away from all this? It's that we have to approach our data not just as number crunchers, but as detectives. Here are the 3 big rules. Rule number 1. For well-behaved, predictable stuff, yeah, trust your averages. More data really does make things better. Rule 2. Always, always be on the lookout for those heavy tails, for the possibility that one rare event can change the entire game. And rule number 3, never, ever forget that more data is not a magic wand. It can't fix a broken model, and it's totally useless if there's no real average to find in the first place. And that really gets to the heart of it. The most important skill in this data-filled world isn't just running the numbers. It's having the curiosity to ask the tough questions about where that data came from, what its shape looks like, and what story it's really telling you. So I'll leave you with this to think about. In a world that seems to be more and more defined by these wild, heavy-tailed events, by stock market crashes, viral videos, and huge disruptions, what does average even mean anymore? And how do we make sense of it all when it's the exception and not the rule that can change everything?